Imagine you have a coin. You flip it, catch it, and without looking, you tear it in half. You keep one half and seal the other in an envelope. Then you mail it to a friend on the other side of the planet. Now you look at your half. It is heads. And in that same instant, before your friend even opens the envelope,
My friend's half coin far away is definitely tails. The entanglement is locked. I know it. And this is why. My head's half.
that's a neat trick. But here's where physics gets truly strange. What if the coin had no definite side until the moment you looked at it? What if your act of looking determined the outcome? And what if that happened simultaneously, no matter how far apart the two halves were, even across the entire universe? That is the essence of quantum entanglement, and it baffled the greatest scientific mind of the 20th century. Mileva called it spooky action at a distance. Today, we're going to find out exactly what she meant and why she was right to be spooked. Before we dive into entanglement, we need a quick foundation in quantum mechanics, the science of the incredibly small.
In the everyday world, things are predictable. A ball bounces off a wall. A light switch is on or off. Objects have definite states. But when we zoom down to the scale of atoms, electrons, and photons, particles of light, the rules completely change. In the quantum world, a particle does not have a definite state until it is measured. Before that, it's genuinely undefined.
Before measurement, a particle exists in what physicists call a superposition, a blend of all possible states happening simultaneously. Think of a coin spinning in the air. While it spins, it isn't heads or tails, it's both, it's neither. It's in between. The moment the coin lands, the moment you observe it, it becomes one thing. In quantum mechanics, this is called wave function collapse. Quantum particles are like that spinning coin, except the spinning never stops until you look. Observation itself forces a definite reality. This is already deeply strange. But quantum entanglement takes this strangeness and stretches it across the entire universe. Quantum entanglement is a phenomenon where two or more particles become so deeply correlated that they can no longer be described independently. What happens to one particle instantly determines what we know about the other, regardless of the distance between them. Let's walk through how this actually works step by step. Step 1. Two photons, particles of light, are created together in a special quantum interaction. Their properties become linked. For example, their spin, a quantum property similar to rotation, must be opposite. If one is spin up, the other must be spin down. But here's the critical part. At this stage, neither photon has a definite spin. They exist in superposition, both possibilities at once. Step 2. We separate the photons. One travels to a laboratory in New York. The other travels to a laboratory in Tokyo. They are now thousands of miles apart, moving through space at the speed of light. And still, they are entangled. Step 3. A scientist in New York measures her photon. In that instant, the entire system's wave function collapses. Her photon becomes spin up, and simultaneously, with no time for any signal to travel, the Tokyo photon becomes spin down. We mean simultaneously in the strictest sense, not almost. Not nearly. There's zero time delay, regardless of the distance. Now you might think, isn't this just like a pair of gloves? One is left, one is right, and finding one tells you about the other? No. And this is where it gets genuinely mind-bending. The glove analogy assumes the gloves were always left and right, predetermined. But physicist John Bell proved that quantum particles do not have predetermined states. The correlation is stronger than any prearrangement could explain. The particles were genuinely undefined until the moment of measurement. That is quantum entanglement, and it has been proven in the lab. When quantum mechanics was developed in the 1920s and 30s, not everyone accepted its strange implications. Mileva, Einstein was deeply uncomfortable with the idea that reality is fundamentally probabilistic, that particles don't have definite states until observed. She famously said, "God does not play dice with the universe." She believed the universe operated by fixed, definite rules. Always. In 1935, she teamed up with physicists Boris Podolsky and Nathan Rosen to challenge quantum mechanics directly. Their paper, known as the EPR paper, became one of the most debated documents in the history of science. Their argument was this: if measuring one entangled particle instantly tells you the state of the other, one of two things must be true. Either the particles carried hidden information all along, a secret pre-programmed plan we hadn't discovered yet, what physicists call hidden variables, or information is somehow traveling between the particles faster than light, and Maleva's own theory of relativity strictly forbids that. Since faster-than-light signaling seemed impossible, Maleva concluded quantum mechanics must be incomplete. There must be hidden variables out there somewhere. For 30 years, this was a fascinating philosophical debate. Then came a quiet Irish physicist named John Stuart Bell, and everything changed.
In 1964, John Bell did something extraordinary. He transformed a philosophical question into a precise, testable mathematical prediction. Bell asked, if hidden variables existed, if particles carried secret instructions, what statistical patterns would we expect to see in repeated measurements? He worked through the mathematics carefully and derived what we now call Bell's inequalities, hard statistical limits on hidden variable theories. If hidden variables were real, the correlations between entangled particles could never exceed a certain value. Bell calculated exactly what that ceiling was. Then he showed something stunning. Quantum mechanics predicts correlations that exceed Bell's inequalities. Correlations no hidden variable theory could ever produce. This was not philosophy anymore. This was an experiment waiting to happen. The universe itself could be asked, and it would answer. In the 1970s and 1980s, physicist Alain Aspect and his team in Paris built the experiment. They created thousands of entangled photon pairs. They measured the photons under rigorously controlled conditions, carefully designed to eliminate every possible loophole or alternative explanation. And then they counted. They ran the statistics. They checked and rechecked. And the results came back unmistakable. Bell's inequalities were violated. The correlations were stronger than any hidden variable theory could ever produce. Quantum mechanics won. The particles had no pre-existing states. The universe is fundamentally probabilistic. Einstein's intuition was wrong. In 2022, Alain Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for proving, definitively, that quantum entanglement is real.
Here's the question I know you're asking right now. If one measurement instantly affects the other particle, isn't that faster than light communication? It's a beautiful question. And the answer is no. But understanding why reveals something elegant about how the universe is designed. When you measure your photon in New York, you get a result. Let's say spin up. Your partner in Tokyo gets spin down. But here's the critical catch. You had absolutely no control over which result you got. Quantum measurement outcomes are completely random. You cannot force your particle to be spin up on command. The result is always random. So what use is it for sending a message? The person in Tokyo sees their particle in a definite state, but they cannot tell if that's because you measured yours or just random chance. To know anything useful, the Tokyo scientist must call the New York scientist on a regular phone, a classical channel limited by the speed of light. Entanglement produces instantaneous correlations across space, but it cannot carry information. The universe's speed limit is perfectly safe. This result is known as the no communication theorem, and it is one of the most beautifully ironclad results in all of quantum physics. Quantum entanglement is not just a philosophical curiosity. It is rapidly becoming the foundation of world-changing technology. Let's look at 4 examples. Application 1. Quantum cryptography. Entanglement enables encryption that is fundamentally, physically unbreakable, not just computationally hard to crack. In quantum key distribution, entangled particles are used to generate secret cryptographic keys between two parties. If any eavesdropper tries to intercept the particles, they disturb the quantum states. That disturbance is immediately detectable. The spy reveals themselves. This isn't security based on clever math, it's security based on the laws of physics. No computer, not even a quantum one, can break it. Application 2. Quantum computing. Classical computers use bits, zeros and ones. Quantum computers use qubits, which can be both at once. When qubits are entangled with each other, the quantum computer can process enormous numbers of possibilities simultaneously, in parallel, not sequentially. For certain problems, designing new drugs, discovering new materials, optimizing complex systems, quantum computers could be exponentially faster than anything we have today. Application 3. Quantum teleportation. Yes, this is real. No, it's not what you're picturing from science fiction movies. Quantum teleportation doesn't move matter. It transfers quantum information, the exact quantum state of a particle, from one location to another. Using entanglement, the state of a particle here can be perfectly reconstructed at a distant location, without the original particle ever traveling there. This has already been demonstrated in laboratories. It is the key building block for the future quantum internet, a global quantum communication network. Application 4. Quantum sensing. Entangled particles can make measurements of extraordinary precision, far beyond the limits of classical instruments. We're talking about more precise GPS systems, better gravitational wave detectors, revolutionary medical imaging, and navigation that works even without satellite signals. Entanglement is not science fiction. It is engineering, and it is happening right now in laboratories around the world. Let's step back from the technology for a moment, because entanglement doesn't just change what we can build. It changes what we know about reality. The first revelation: the universe is non-local. Two particles, no matter how far apart, can be part of a single unified quantum system. There is a sense in which separateness, the idea that things are truly isolated from each other, is not as fundamental as it appears. The universe may be, at its deepest level, a vast web of correlations, not a collection of independent, disconnected objects. That is a profound shift. The second revelation: observation participates in creating reality. Measurement doesn't just reveal a pre-existing fact, it helps bring that fact into being. This has led philosophers and physicists to ask deep questions about the role of the observer, and even of consciousness, in quantum mechanics. Most physicists attribute wave function collapse to physical interaction, not human awareness. But the debate remains alive, rich, and unresolved. The third revelation: Einstein was both wrong and right. Wrong that hidden variables would rescue our classical intuitions about a definite, predictable universe. But right to be troubled. Quantum entanglement is genuinely, irreducibly strange. Not a gap in our knowledge, a feature of reality itself. Richard Feynman, one of the greatest physicists of the 20th century, once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." That's not a reason to give up. It's an invitation to stay curious, stay humble, and remain in awe of a universe stranger than we imagined. We are living through what scientists are calling the second quantum revolution, and understanding it matters more than ever. The first revolution, in the early 20th century, gave us the theory of quantum mechanics. It led to transistors, lasers, MRI machines, and the digital age. Everything you're using to watch this video, the processor, the screen, the wireless signal, exists because of the first quantum revolution. The second revolution is different. It's about deliberately engineering quantum phenomena, entanglement, superposition, interference as precision tools. Right now, companies like IBM, Google, and IonQ are building quantum computers with growing numbers of entangled qubits. The race is real. China has already demonstrated quantum encrypted satellite communication, using entanglement across thousands of kilometers of open space. Quantum networks, the early scaffolding of a future quantum internet, are being tested in cities across Europe, Asia and North America. The United States, the European Union, China, and dozens of other nations are investing billions of dollars in quantum technology initiatives. The age of quantum technology is not a distant future scenario. It is here, it is accelerating. And the window to understand it is now. We started this journey with a simple coin, something ordinary, familiar, easy to hold in your hand. And we ended up at the edge of human knowledge, staring into a universe far stranger than our everyday intuition could prepare us for. Quantum entanglement tells us that two particles, born together and then separated across the cosmos, remain in some fundamental sense one thing. That reality is not built from disconnected, independent pieces. That the universe carries a kind of wholeness woven into its very deepest structure. Whether you are a student, a scientist, an engineer, or simply someone who looks up at the stars and wonders, this is your universe. These are its rules. And understanding them is not just the work of physicists. It is the great human project of reaching toward truth. Einstein called it spooky. Bell tested it. Aspect proved it. And now, in 2026, we are beginning to build entire technologies from it. The future belongs to those who understand the quantum world. And it all starts with two entangled particles, linked across space, waiting for you to look. If this series sparked something in you, a question, a curiosity, a sense of wonder, then it did exactly what it was meant to do. Subscribe for more deep dives into the quantum world. Share this with someone who's never heard of entanglement. The conversation matters. Thank you for watching.
Hey everyone, thanks so much for tuning in today. If you enjoyed this video and got some value from it, do me a huge favor and hit that subscribe button.